Namaskar. So, in last class we were discussing about the transformer polarity. So, we will continue our discussion. So, let us see the transformer polarity which we discussed in the last class. We discussed that it is important to get the polarity of the voltage and the direction of the current for the transformer. Now, the polarity of voltages that is on primary and secondary side of the transformer and the direction of current I1 I2, that is again primary current and the secondary current. So, if the polarity or the direction of the current changes, the transformation ratio, that is N, may need to be replaced by minus N. How we will decide whether it will be N or minus N? We will follow these two simple rules. So, what are those rules? If V1 and V2 are both positive or both negative at the dotted terminals, we use plus N in the transformer voltage equation, otherwise we will use minus N. So, if one is positive, other is negative, then we will use minus N instead of plus N. Now, if current I1 and I2 both enters into the dotted terminal or both leave the dotted terminal, we use minus N in the transformer current equation, otherwise we will use plus N. So, using these two rules, we can figure out that there are 4 possible combinations. So, we discussed in the last class that these will be the 4 combinations where the voltage polarity is same, that is why V2 by V1 is equal to N2 by N1, that means equal to plus N. Here I2 by I1 is also N1 by N2, because the one is going inside the dotted terminal, other is coming out from the dotted terminal. In the second case, the transformer voltage polarity is same, that is why V2 by V1 is equal to N2 by N1. The direction of current is changed, that is why I2 by I1 is now become minus N1 by N2. In the third figure, here you see the polarity of voltage is changed, that is why V2 by V1 will become minus N2 by N1. Current will be I2 by I1 is equal to N1 by N2. Why? Because one is going inside the dotted terminal, other is coming outside of the dotted terminal. So, your I2 by I1 will become N1 by N2, the same as we saw in this figure. Now, in the fourth case, you will see the polarity for voltage is changed. So, that is why it will become V2 by V1 is equal to minus of N2 by N1. Current is also changed, because one is going inside the dotted terminal, at this point also it is going inside the dotted terminal. So, I2 by I1 will also become minus N1 by N2. So, this is what we discussed in the last class. Now, let us see other aspects of the transformer. Using transformer voltage and current transformation equations, we can now represent voltage, that is primary side voltage, in terms of secondary side voltage, and primary current in terms of secondary current, or vice versa. So, what we can say? We can say V1 is equal to V2 by N with the help of transformation ratio, and we can also say V2 is equal to N V1. Similarly, in case of current, I1 is equal to N I2, or I2 is equal to I1 by N. Now, let us see complex power in the primary winding of the transformer. So, what will be the complex power? Complex power will be V1 I1 conjugate. So, if you put the value of V1 I1 in terms of V2 and I2, V1 will be V2 by N, and I1 will become now N into I2. So, when you simplify, you will again get V2 I2 conjugate. So, what you can say that complex power supplied by the primary is delivered to the secondary winding without any loss, because we have considered transformer as a lossless equipment and ideal. So, transformer will absorb no power. Now, this is anyway expected, because in case of ideal transformer, you will take transformer as a lossless equipment. Now, the input impedance, if you see that input impedance, if you see from the primary side, that is Z in will be nothing but V 1 upon I 1, or you can convert it in terms of V 2 I 2, this will become 1 by n square V 2 by I 2. Now, at the secondary side, if you connect the load, so if you connect load at the secondary side, say ZL, so what will happen in that case? Your V 2 by I 2 will become equal to ZL, and in that case you can say Z in, that is input impedance from primary side, will be equal to 1 by n square ZL square. So, not ZL square, so ZL. So, basically the input impedance is also called the reflected impedance, because it appears as if load impedance is reflected or referred to the primary side. So, sometimes you will see in the literature it is written as the load impedance reflected to primary side, and somewhere you will see that it is written as load impedance referred to the primary side. So, both are correct. So, in that case what you will do, you will take the load impedance, convert it as if it is connected to the primary side. So, now this ability of the transformer to transform a given impedance into another impedance will provide us a means of impedance matching, which will ensure the maximum power transfer. Now, let us take a couple of examples related to the ideal transformer to understand the concepts which we have discussed till now. Now, if an ideal transformer is rated as 2400 by 120 volt and the kVA rating is 9.6 kVA, has 50 turns on the secondary side, we need to calculate the turns ratio and the number of turns on the primary side and current ratings for primary and secondary windings. Now, since V 1, that is 2400 is greater than V 2, that means that we are talking about the step down transformer, N will be V 2 by V 1. So, you get turns ratio as 0.05. Now, based on this you can find out the value of number of turns on the primary side, because N is nothing but N 2 by N 1, N 2 is given as 50. So, you will get N 1 as 1000 turns. Now, we know the kVA ratings. So, as that is the rating of the transformer is V 1 I 1, or it is also equal to V 2 I 2 and given as 9.6 kVA. So, what will be the value of current? Current will be 9600 divided by V 1 will be 4 ampere, and I 2, that is secondary current, will become 9600 divided by 120, that is 80 ampere. Now, suppose if the ideal transformer contains the circuit as shown in the figure below, we need to calculate the source current I 1 and the output voltage V 0 and complex power supplied by the source. So, in this case you will see that the 20 ohm is the load impedance. So, to simplify it, what we have to do, first we have to convert that load impedance in such a way that it is reflected to the primary side. So, how we will do it? Suppose ZR is the reflected impedance, you can write 20 divided by n square. So, you will get 5 ohm as a reflected impedance. Now, when you reflect this to the primary side, the total impedance of the circuit will become now 4 minus J6 plus ZR, which you have got equal to 5 ohm. So, now the total input impedance from seeing from primary side will be 10.82 angle 33.69 ohm. So, therefore, current I 1 will be the voltage V 1, that is 120 degree angle 0 divided by the input impedance, and when you simplify you get I 1 is equal to 11.09 angle 33.69 ampere. Now, here I 1 and I 2 both are leaving the dotted terminal. So, here you will see that this will leave the dotted terminal, here also it is leaving the dotted terminal. It means the I2 will be minus 1 by n I1. So, this will become minus 5.45 angle 33.69 ampere. So, what will be the V naught? V naught will be the R into I2. So, it will become 110.9 angle 213.69 ampere. So, what have been done here, since we have the minus sign. So, this minus sign has gone inside the angle value, because minus 1 is nothing but 1 angle 180 degree. So, if you take the minus out and multiply by 1 angle 180 degree, simplify, you will get 110.9 angle 213.69. So, this is how you have got the angle value different from the what we have seen in case of I2 when minus sign was present. Now, next is how much complex power is being supplied. So, source voltage we know, current I1 we have calculated. So, for finding out the complex power, we will take the conjugate of the I1. So, this will become 120 angle 0 as Vs, I1 will become 11.09 angle minus 33.69. So, to after taking conjugate, this angle will become negative. So, it will become minus 33.69. So, now when you simplify, you get the value of complex power as 130.8 angle minus 33.69 volt ampere. Now, let us start another topic which is 3-phase circuit. So, till now what we have discussed in our course was basically related to single phase circuits. So, in case of single phase AC power system, we consist of one generator connected through a pair of wires, or we call it as transmission line, and this line is connected to load. So, that means if you see this particular figure, this is a single phase AC power system where you have voltage source connected to the load with the help of the pair of wires. So, we call them as a transmission line. Now, here Vp is nothing but the RMS magnitude of the source voltage, and phi is the phase angle, and ZL is the load impedance. Now, there are circuits or systems in which AC source operate at the same frequency, but there may be different phases. So, we call them as a polyphase circuit. So, if you see the figure below, you will see on the left there are two voltage sources connected to the load with the help of 3 transmission lines, and load ZL1 and ZL2 are connected. So, if you see these two sources, one is Vp angle 0 degree, another is Vp angle minus 90 degree. So, both are operating at same frequency, but the and also the RMS value of the voltage magnitude is same, but angle is different. So, this is basically our 2-phase 3-wire system, where we see the phases are 2 in the quantity. So, 2 different phases are connected to this circuit, and in this figure which is on the right, you will see there are 4 wires. So, we say them A, B, C and N. So, these we can say as A phase, B phase and C phase, and then the neutral wire. Now, these 4 wires are connecting the 3 voltage sources to the 3 loads. So, loads are ZL1, ZL2 and ZL3. Voltage sources are having same frequency and same RMS voltage, but the phase values are different. So, in this case you will see phase value is 0 degree, in phase B you will have phase value minus 120 degree, and in C you will have phase value as plus 120 degree, or you can say phase value is minus 240 degree. So, basically here you will see that the 3 sources are having 3 different phase value. So, this particular set of circuit is called 3-phase 4-wire system, because we have 3 phase output and 4 transmission lines are required to connect to the load. So, in these cases you will see that the sources are more than one and number of wires are also more than 2 to connect to the load. Now, as distinct from the single phase system, the two phase system which we saw in the left side of the previous slide is produced by generator consisting of 2 coils placed perpendicular to each other. So, the coils which will be arranged in the generator will be 90° out of phase. So, those will be perpendicular to each other, so that the voltage generated by one leg coil lags the other by 90°. So, in the same way, in case of 3 phase system, the generator will have 3 coils. So, you can say that there are 3 different sources having the same amplitude and frequency, but they will be out of phase by 120°. Now, since 3 phase system is most prevalent in and most economical polyphase system, so that is why you will see in the normal power system network most of the time the power is being supplied through 3 phase system. So, in our particular discussion we will concentrate more towards the 3 phase system. Now, 3 phase system is very important because there are 3 major reasons of that. First, the electric power which we get in our houses or in our industrial establishments are mainly the 3 phase power. So, in houses you will have single phase output of this 3 phase power, but in industrial establishment you will directly see that 3 phase power supply is given to run the big loads, and all these operating either at 50° or 50 hertz or 60 hertz. Now, the instantaneous power in a 3 phase system can be constant. That means that when you power the voltage or the power is being generated from the generator, the value of power P, that is average power, will always be constant. So, this particular phenomena we will discuss in later our course, that how we can say that the power which is generated from the 3 phase system is constant. Now, 3 phase system is more economical than the single phase system. Why? Because the amount of wire which is required for a 3 phase system is lesser than the amount of wire needed for an equivalent 3 single phase systems. So, let us see how we generate balanced 3 phase voltages. So, if you see the cross section of the generator, how you generate the 3 phase power. So, if you see that there are 3 set of windings are arranged in the stator side of the generator. So, how they are wind? The A is connected like this in such a fashion that this will be a coil for A dash set. Similarly, for B dash set you will have one set of coil arranged like this. So, this will be wound. Similarly, for C also you will have these set of coils. So, basically you will have 3 sets of coils which are 120° apart, and when the magnet which is rotating in the generator will cut the coils, you will get the voltage induced in these coils. So, generally these rotating magnets are either permanent magnet, or you arrange the coils in such a way that you get the rotating magnet in the generator. So, since these all 3 windings are 120° apart, you will get 3 phase power as a output. Now, these separate winding or coils which you see as A dash, B dash, C dash in the figure. So, basically we arrange the coils in such a way that it completes one set of arrangement for one particular phase. They are physically 120° apart around the stator. So, if you see A and B, so the angle difference will be physically 120 degree. Similarly, between B and C and between A and C will be also 120 degree. So, your windings are now physically apart by 120 degree. Terminals A dash, let us take first A and A dash for example, stand for one end of the coil goes into the other end coming out of the slides. So, what we can see, we have wound, as I shown, that we have wound in such a way that the coil goes inside and then comes out and goes inside and so on. So, you can take multiple number of turns based on the voltage output which you want from the generator. Now, when the rotor rotates, as we saw that when you rotate the rotor, the magnetic field will cut the flux from these coils and the voltage will be induced in these coils. Now, since the coils are placed 120 degree apart, the induced voltage in the coils are also equal in magnitude, but will be out of phase by 120 degree. So, when the moment you see the magnet is cutting phase A coil, so that is A dash coil, you will see that the voltage is being building up in the coil A. So, when you see in this figure, if you start from A, then if you move to B, that means that after 120 degree the voltage will start building up in B coil. So, you will see now the voltage is started building up in B coil. Similarly, after another 120 degree, you will see voltage is now being building up in the C coil. So, now all these three phases are 120 degree apart and the output which you will see in the individual coil is almost sinusoidal. Now, since both coils can be arranged as a single phase generator by itself, the three phase generator can supply power to both single phase and three phase loads. So, if you see this particular figure, so these three coils are independent coils. So, you can consider them as a three independent sources. So, what you can do, you can arrange them in such a way that it looks like there are three different voltage sources. So, if you see this particular figure, the generator is wound in such a way that it is star connected. So, in that case you will see that phase A, phase B and phase C can be considered as three independent voltage sources, and if you have neutral coming out of the generator, so you can have three single phase created out of three phase arrangement. So, neutral and A will create one phase, B and N will again create another phase, and C and N will create another phase. So, now you will have three phase system which will give you also three independent single phase systems. So, this is typically visible in case of you have three phase or three phase and four wire systems. Now, if you have three phase three wire system, you will arrange the sources in such a way that it is looking like a delta connected arrangement. So, in that way you will have three phases as an output, which you will see in the figure. So, now you can arrange the voltage sources either in star connected. So, you also call it as Y connected and delta connected. Now, let us consider the star connected that is Y connected voltage for now. So, here we will have phase voltages as VAN, VBN and VCN. So, these are respectively the voltages between line ABC and the neutral. So, we have seen that VN is nothing but voltage between A and N lines, VBN is between B and N, and VCN is between C and neutral. So, now these voltages are called phase voltages because you have taken them with respect to neutral. So, if the voltage source have the same amplitude and frequency and are out of phase with each other by 120 degree, the voltage are said to be balanced. So, the criteria for balanced voltage output is that the voltage magnitudes should be same, frequency should be same, and all should be 120 degree apart from each other. So, if you see this particular figure, all our voltages are 120 degree from each other. So, now when you see this particular arrangement, you can simply say that VAN plus VBN plus VCN is equal to 0. So, if you take voltage at any point, say if you see at this point, you will see that the total sum of voltage will be 0. So, you can see at any point you will get the value of VA plus VBN plus VBN plus VCN will always be 0, and this is again the criteria for a balanced system. So, when the voltage source is balanced, you will get VAN is plus VBN plus VCN equal to 0. So, that is in phasor form, but in magnitude form, since we have same amplitude, we will get VAN equal to the mod of VAN equal to mod of VBN equal to mod of VCN. So, what we can say now, the balanced phase voltage are equal in magnitude, but are out of phase with each other by 120 degree. So, now since the voltages are 120 degree out of phase, there are two possible combinations for the arrangement of these phases. So, in one such arrangement is shown in this slide, where VAN is leading VBN by 120 degree and VBN is again leading VCN by 120 degree. So, what you can write, if you write in terms of phasor, VAN you can write as VP, that is RMS value of the voltage angle 0 degree. VBN you can write VPN angle minus 120 degree. VCN you can write VP angle minus 240 degree, or you can say VP angle 120 degree. So, here VP is the RMS value of the voltage. Now, here the common tradition in the power system is the use of RMS values. So, in this module also the voltage and current we will consider in RMS values or otherwise stated in the particular discussion. So, what we get here, we get ABC sequence or the positive sequence of the phase arrangement. So, here if you see VA, VB, VC are arranged in the direction of the rotation of the air gap flux. So, in that way if you see basically the rotor and stator will create one flux which will cause the rotation of these phases. So, VA, VB, VC you will see will be arranged in such a way that it is counterclockwise. So, in that way you can say that the particular VA, VB, VC arrangement is called as ABC sequence of the phase arrangement, or you can call it as a positive sequence arrangement of the phases. So, here we have seen that VAN leads VBN and VBN leads VCN. This sequence is produced when rotor, we have just seen that it is rotating in the counterclockwise as we have seen from the figure. Now, this phase sequence may also be regarded as the order in which phase voltage reach their peak value with respect to time. So, if the arrangement is like A, B, C, so you will see first A will reach its peak value, then B will reach its peak value, and then C will reach its peak value in this particular phase arrangement. Now, there is another phase combination where V, that is the phase A voltage, leads phase C voltage by 120 degree, and phase C voltage leads phase B voltage by 120 degree. So, in that case what you can write? You can write VAN is VP angle 0. So, we consider A as a reference, then VCN is VP angle minus 120 degree and VBN is VP angle minus 240 degree, or you can say the VP angle 120 degree. So, here now the sequence is ACB sequence, or you generally call it as a negative sequence. So, in this case VAN leads VCN and VCN leads VBN by 120 degree. Now, so sequence is produced when rotor is rotating in the clockwise direction. So, here now if you calculate VAN plus VBN plus VCN, so you put all the values in their respective phasor notation. VAN will be VP angle 0 degree, VBN will be VP angle minus 120 degree, and VCN will be VP angle 120 degree. Now, if you convert them into rectangular form and sum up, you will always get the summation of VAN, VBN plus VCN will be equal to 0. So, the phase sequence is determined by the order in which phasor pass through the fixed point in the phase diagram. So, I think with this you can understand that how ABC and ACB sequences are arranged. So, ABC is considered as a positive phase sequence and ACB is considered as a negative phase sequence. So, with this we can close our today's discussion at this point. We will continue our discussion related to this 3 phase network in our next section also. Thank you.